Well, there's good news here that when we go to talking about velocity and acceleration using vector functions, 3D sort of things, it's very similar to velocity acceleration that we've talked about in the past, right? Because we had, usually we had like an S or an S of t, and that was, that described a position at time t, whether it be, you know, a height or, I mean, it could just be like a particle. We talked about a particle bouncing maybe around in linear sort of fashion, but whatever it is, somehow that describes position, whatever position that is. Well, if we did then the derivative of that, well, that gave us the rate of change of the position, which turned out to be another use, I guess you might say, another application of the derivative, right? So this would equal the, call it v of t, the velocity at time t. So yeah, that's what we had before. Then if we took the derivative of the velocity, well, that's the rate of change of the velocity, which the rate of change of velocity, another way you could look at that is acceleration, right? So that was what we saw as far as the derivatives go of position and then the derivative of velocity. The one other, no, okay. So if I translate that over to vectors then, so if I have a particle moving about in space, it could be two-dimensional, three-dimensional, still could do two. I think they have some still doing 2 dimensions, but 3 dimensions or whatever, 4 dimensions, it doesn't matter. The position is, if we say the position vector is r of t, so we can use a position vector to describe the position of a particle or an object. Same idea. Guess what r prime of t would be? It's the velocity, right? V of t. And so that would give us a velocity vector at time t. Now, one thing more that we add on to this because of you know, the nature of vectors and so forth. If you talk about the magnitude of v, that is what's described as just the speed. Velocity in some ways is directed speed. You know, like on this one here, you know, sometimes when we do the position, like when you throw the ball upwards or downwards, well, when you do the derivative on the way up is usually the way you have positive velocity, and then on the way down you have negative velocity. So it's, like I said, kind of directed speed. Well, we can talk about speed when we have it in vector form because, yeah, speed is just the magnitude of your velocity vector. So if it asks for speed, you're just going to do the magnitude of the vector. And then if we do the derivative of the velocity vector, well, just like when we did the derivative of the velocity over there, that gives us the acceleration vector. Call it a of t. So, yeah, just in vector format. So nothing really new, right? Just that now we're describing them as vector value functions instead of just regular functions, but it is very much the same. All right. So that's good, right? No change. We like that. All right, so here's our problem. Find the velocity, acceleration, and speed of the particle spell particle with r of t. The position function is t plus 1 I plus t squared minus 1 j plus 3k. All right, so yeah, it's just like we hoped. The velocity vector, that's just the derivative of the position vector, r prime. And so, again, to do r prime, you just do the derivative of each particular part. So in this case, it would be what? 1i plus 2tj plus 0, okay. That's it. I guess we go in order then. Let's go. All right, so what would be the speed here? Well, the speed is just the magnitude of the velocity vector. And so that would be here 1 squared plus 2t squared plus 0 squared. That's 0, but we get the square root of 1 plus 4t squared. And so, yeah, your speed, these for these vector value functions, usually you're going to get just a function of t. Put in the t there. And then, of course, the acceleration, a of t vector, is just the derivative of the velocity vector. So that would be 0i plus 2j plus 0k, so it's just 2j. Would be your acceleration vector for that particular example. All right, now, they will also have you on these problems here do something like this. All right, so let's sketch the path of the particle. Excuse me. And draw the velocity and acceleration vectors for t equals 1. Yeah, so we'll talk more about sketching along the way as we go along here, but here's another one. We did the helix, and as far as three-dimensional things, we've done helix and sphere. I guess we talked about the sphere a little bit, but here's another one. Just another example. Sketch the path of the particle. All right, so here's our path of the particle is the vector function, and when you go to sketch the graph, really it's sketching the parametric equations associated with that, and so x would be t plus 1, y would be t squared minus 1, and then z, you just bunch there, z equals 3. And let's just talk about that. This is nice because the z value doesn't, so if I'm thinking about the XYZ plane here, coordinate system, the Z value is locked in to be 3. And so whatever happens in terms of X and Y, the Z value is always 3. So that basically what you've got is you've got this curve and the height is at 3, if we think about this coordinate system, right? Now, what does this do in terms of the X and Y plane? Well, if we just look in the XY plane here, you've got these parametric equations, but probably the easiest way, I mean, you can grab those on your calculator, but probably the easiest way to think about it here would, if I get this instead of parametric equations, get it in the Cartesian, the XY Cartesian equation form. Let's see, x minus 1 would be t, and so I could plug that in for t here, and that would be y equals, so take this and plug that in for t there. So you got y equals t, x minus 1 squared minus 1. And so that's pretty easy to see. That's just a parabola, 1 to the right, 1 down, right? Vertex would be there. So that's what it looks like in the XY plane. Well, the XY plane here is, like this, flat out like that. So we've got this in the XY plane, so that would be, if it was at a height of 0, it'd be in the, it's not actually in the XY plane. When we go here, the height is 3. All right, so if I think about that, but at a height of 3, so it's, what do we say, 1, it'd be here, and then 1 unit back. So yeah, so it's kind of up in here. Parabola, flat this way. It's hard to draw in 3 dimensions and 2 dimensions. But you get the idea. All right. So this point here is 1 this way, and then 1 here, and then back 1 here. So yeah, it's kind of out there. Kind of get the idea there. All right, so it's a parabola, but it's 3 units high. Kind of system. All right, so that's another example of a 3-dimensional drawing. From time to time, we'll try to do some of those. But all right, so now the other thing was I wanted to sketch the velocity and acceleration vectors at t equals 1. So what these give me, the velocity and the acceleration, those just give me vectors that I could technically, I guess, sketch those vectors anywhere I want to, but let's actually put them at the point that's associated with t equals 1. So what point on the graph are we talking about? In other words, what's the position of the particle at t equals 1? Where are we talking about there? Well, at t equals 1, we'd have x is 2, y is 0, and z is 3, right? So x is 2, y is 0, and then z is 3, so we're talking about somewhere along in here. I didn't do probably just a really good job of drawing that, but 2, 0. So it's up above this, wherever it comes out. So that's our position. Now the velocity vector at 1, what would it be? It would be 1, 2, 0. So that's 1 in the I, 2 in the J, nothing in the K direction. So that would be, so we go 1 this way, and then 2 this way, right? So from the, if I use that as my initial point, I would go 1 in the X direction, which is here, and then 2 in the Y direction, which would be 2. So I'd be pointing out somewhere, it's kind of hard, something like that. And then it's easier in 2 dimensions, obviously. I was going to try to do 1 and 3 because I think there is 1 and 3 on your homework. So the acceleration then at t equals 1. Well, that's easy. It's just 2j. They're all the same. And so you don't go anywhere in the only direction you go in that one is just 2 in the j direction or the y direction. So that would be at this point, and then you just go 2 back. So that would be, so this is your V at 1, and that would be your A at 1. So anyway. Something. Any questions about that one? All right, now, this next one here, let's kind of work our way backwards. Here's what. All right, so let's find the velocity and position of vector functions. So find the velocity and position vector functions of a particle with acceleration vector a of t equal 4ti plus 6tj plus k. And there's some other information. And initial position r of 0 equals just I. And initial velocity v0 is I minus j plus k. So we've got the initial position, and we've got in vector form, and then we've got the initial velocity in vector form. So let's see what that is. Okay. So like I said, this is basically we're going backwards here, are we? The previous one we had the position, we got the velocity by doing the derivative, and then the derivative of the velocity gave us the acceleration. Well, here we're starting with the acceleration, and we want to work our way backwards to the velocity and then ultimately to the position. Well, so here's what I know. A of t is equal to the derivative of the velocity. Well, then it stands to reason the velocity would be, so if I start with the acceleration and I want to get back to velocity, doesn't it stand to reason if I do the derivative to get this one, I do the antiderivative of this to get back to the velocity. So I'm going to integrate a of t dt to get back to my velocity. So let's just enter. All right, so in this case, the velocity would be the integral of a of t, so it would be the integral of 4ti plus 6tj plus k dt. All right, and so we would, nicely, the way you do that is you just do the antiderivative of each individual part. So the I part, the antiderivative there would be what, 2t squared? 2t squared I. The antiderivative here would be 3t squared j. And then the k component is just 1, so the antiderivative of that would just be t. T times k. Now the little catch on this one is it's an indefinite integral. The previous integrals we did with these vector functions, they were, we knew the upper and lower limits. We had those, so we didn't have to factor in a constant. Well, this is a indefinite integral, so we have to think about a constant here. And so usually what we do is we think, so this is plus some constant vector, which means it could have an I, J, K component, if we're talking about those three. All right, with me there? You have to add in a constant because it's indefinite. Now, so that's our initial findings of V of t, vector V. Well, that is why, that constant thing, that's why it provides us here this initial velocity, because if we have this initial velocity or some known velocity vector already, we can figure out what the constant vector is. So we don't have to leave it just as a constant vector. Yeah, with this we can get this. Well, all right, so if I plug in, notice here if I plug in, so I need to plug in 0 to kind of match these two up. What is V of 0 here? If I plug in 0, it's just C, isn't it? Yeah, because all those, the T is 0, so all those would zero out. So the V0 is the constant. In this case, it is the constant vector. And so I know V0 is ijk, so C is I minus j plus k. So that, in this particular case, gave me directly what C was. Now, how does that factor in? So, well, if I put that in to my little vector function here, I now know C is I minus j plus k. Well, can I combine the I parts, combine the j parts, combine the k parts? So V of t would be 2t squared plus 1. That would be the I part. And then the j part would be 3t squared minus 1. And the k part would be t plus 1. Okay? So that's our V of t. So that's the first part now. Now I need the position vector function. Well, I know that V of t equals r prime of t. So following the same logic here, if I do the r of t, to get r of t, if I know the velocity function, r of t would be the integral of the v of t, wouldn't it? So I go step back, if you will, go the other way with that. Yeah, if I do the integral of that, that'll give me r of t. So r of t is the integral of my vector function, which is what I've got down there. 2t squared 2t squared plus 1i plus 3t squared minus 1j plus t plus 1. Okay. So take that integral right there, and that'll give you your position vector function. So what does that give me? 2/3 t cubed plus t I plus antiderivative, that would be t cubed minus t j plus 1/2 t squared plus t k. But again, it's an indefinite integral. Yeah, so I need to add, and usually, I mean, we can use c again, but usually they, since we use c for that one, we use d for this one. But it's a constant vector. C1, C2, something like that. All right, but again, here's what we could figure out that d vector, because I've got the r0 is I, and again, r0, if I do it, if I plug in the 0, yeah, that again, that's 0, that's 0, 0, so r0 equals d, so since I know r0, I know d is going to be I. 1i. So if I plug that in, make that my d, doesn't that make r of t then? It really just adds, it adds just 1 to the I, right? So it'll be 2t cubed, 2/3 t cubed plus t plus 1 I. And then d has no j and k component, so it doesn't change those. Is that all right? T cubed minus tj, and then plus 1/2 t squared plus t k. Ta-da.